Now we are ready to argue for the equivalence of our random access model and the traditional Turing machine. To translate between the symbol representation of the Turing machine and the numbers of RAM, we'll use a one-to-one correspondence, E. Note that E of the blank symbol is 0. That way the uninitialized parts of the tape correspond to uninitialized parts of RAM. First, we argue that RAM can simulate a single-tape Turing machine. The role of the tape played in the Turing machine will be played by the memory. We'll keep track of the head position in a fixed register, say R1. And the program and the program counter will implement the transition function. Here I've written out in pseudocode what this might look like for the simple Turing machine shown over here, which just replaces all the 1s with 0s and then halts. Being in state Q0 corresponds to having the program counter point here. So the RAM will execute a sequence of tests for what the symbol under the head would be, and it adjusts the values of the tape and memory accordingly. Sometimes just moving to the right by changing the value in this register, and then saying, hey, let's return to state Q0, or sometimes a write is necessary, say for this transition here, and then again we need to move the head to the right, and then transition back to state Q0, and sometimes we need to move to a new state, like when we encounter the blank symbol, and then in QAccept we halt. Now we argue the other way, that a traditional Turing machine can simulate a RAM. Actually, we'll create a multi-tape machine that implements a RAM, since that's a little easier to conceptualize. Of course, anything that can be done on a multi-tape machine can be done with a single tape, as we've already seen. We will have one tape per register, and each tape will represent the number stored in the corresponding register. We also have another tape that's useful for scratch work in some of the instructions, the ones that involve constants like add 55. Then we have two tapes corresponding to the random access device. One is just for input and output, and the other is for simulating the contents of the memory device during execution. Storing the contents of the random device is the more interesting part. This is done just by concatenating the index value pairs using some standard syntax, like parentheses and commas. The program of the RAM must be simulated by the state transitions of the Turing machine. This can be accomplished by having a subroutine or sub-Turing machine for each instruction in the program. The most interesting of these instructions are the ones involving memory. We simulate those by searching the tape that stores the contents of the RAM for one of these pairs that has the proper index, and then reading or writing the value as appropriate. If no such pair is found, then the value in the memory device must be 0, and we can write a new pair if it's a write instruction. After the work of the instruction is completed, the effect of incrementing the program counter is achieved by transitioning to this state corresponding to the start of the next instruction. That is, unless the instruction was a jump, in which case that transition is affected. Once the halt instruction is executed, the contents of the tape simulating the random access device are copied out onto the I/O tape.